Hello. Yes. Can you hear me? Okay. 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 Thank you. Thank you.
நான் ஆரம்பிக்கல சார். ஆஹா, இது அப்படியே இருக்குது. நான் ஆரம்பிக்கல.
Thank you for the nice introduction. I hope everyone can hear me and everyone can see my slide. And I want to express my apology regarding the camera. So my camera is not working, unfortunately. But however, you can able to see my presentation and my voice is clearly, I hope. Okay, and thanks for organizing committee for this invited talk, especially Dr. Leela, our senior from Bharat. Yes, yes. Oh yeah, hold on, hold on. Yeah, yeah. I think now it will be better, I guess. Okay. Uh, yeah. Okay. So Thanks for the invitation for this presentation, and I would like to express my sincere gratitude to Dr. Leela for inviting me to give this talk. And today's talk will be on the recent research because my postdoc and PhD research will be based on organic light emitting diodes, which I no longer working now, but for the past 5 or 6 years I'm switching to the sustainable energy research. So, in this context, the current presentation will discuss the recent research works we are doing, and in that, I would like also to introduce this topic to other persons who are not expertise in the electrocatalysis research. Okay. So, in that perspective, I would like to discuss the basic design principle and how to evaluate the certain catalysis system with respect to certain electrochemical reactions. And I will also touch slightly towards the carbon dioxide valorization, which is very much needed in the for the sustainable energy research. And most of my talk, like 75 percentage of my talk will be related to green hydrogen and 25 percentage is related to valorization. So, okay, can you see my second slide, right? Yes. Okay. Okay. So the outline of the talk will be as follows. Start from energy landscape. Like in the energy landscape means why we need to go for the alternate energy or the renewable energy. And the next we will discuss about the kinetic and thermodynamic bottlenecks. So, for example, from the discussion of the energy landscape, we will get to know that the water splitting and CO2 reductions are mandatory for the futuristic sustainable energy society. In that case, what are the real issues, real hurdles we have? So that we will discuss in the second section, and then we will try directly hop into the design principles and evaluation. So in that case, we will divide this section into two categories. One is oh, hold on. Okay. Okay, got it. Okay, so the design principles will the evaluations part will be divided into two sections. One will be dedicated to electrocatalysts for water splitting, and we will discuss the basics pertaining to that, and we will discuss some notable works from our research group. And then we will the second section will be dealt with the photo reduction strategies for the carbon dioxide reduction. Okay, and the CO2 reduction can be done with the electro reduction as well as photo reduction, but we will focus only on the photo reduction which we currently doing in our research work. And then finally we will do the summary and future outlook. So the energy landscape or the research background of our research is based on the energy requirement, because the energy requirements of the India will be increased 2.5 times in the year by the year of 2047. So this statement is not declared by me. This statement is declared by one of the specialists from the Niti Aayog. You know the Niti Aayog meeting held in Delhi yearly once or something, right? All the specialists, especially uh, members from various states, will participate. So in that, this declaration is given. So in that case, why the energy requirements will be increased? Because of the urbanization, population, these energy requirements will increase. So the one while the energy requirements are increases, there is a as a side effect, we also have some issues like climate change, natural disasters, and why the climate change and natural disasters occurs? Because most of the today's energy we taken from fossil fuels. The fossil fuels are nothing but the carbon footprint in the bottom of the earth or somewhere we taken, and we steam reformed that into a form of energy, in the form of electricity or anything. So by doing this steam reforming or any other reformation of the carbon footprint getting from the earth surface, the whole chemical reactions will yield several amount of carbon dioxide. So once the carbon dioxide emission is increases in the air, you know the greenhouse effect, right? We studied in the schools itself. So once the carbon dioxide emission is increasing, it will increase the global temperature. So once the global temperature increases, El Nino, Paul Nino, all the effect will come. So it will change our climate, and it will change our monsoon season into a summer, and summer into a monsoon season. So many dramatic changes will occur. So two things we need to address in this for the sustainable society. We need to address two things. One is we have to take some effort to compensate the energy crisis, and we also need to solve or mitigate the carbon dioxide emission, because since 84% of the energy comes from the fossil fuels, we can reduce that percentage and we can introduce some other energy production methods. Or in parallel, we also have to focus on ways to mitigate or reuse that waste carbon dioxide into a useful one, or reduce the amount of carbon dioxide. So these two things are our sustainable energy goals. And in that case, United Nations, the popular guy, one of the secretary from the United Nations also claimed that whether you like it or not, fossil fuels phase out is inevitable. So like he want to move the fossil fuel dependency of energy production out of the equation. So for that, this is not completely impossible. Okay, that is what he said. The fossil fuel phase out is inevitable. What one point of time, maybe 50 years or 100 years from now, we completely stop the fossil fuel based energy protection, and we need to depend more on renewable energy sources. That is his statement. And India will and the Prime Minister of India also claimed that India will reach its non-fossil fuel energy capacity of 500 gigawatt by 2030. So it is like Abdul Kalam's dream, but our Prime Minister dream also in the 2030 is to reach 500 gigawatts of energy capacity in India without the use of fossil fuels. Because once we use the fossil fuels, again energy, the CO2 emission and all other issues will come. So that is why we have to look for an alternative. So when you speak of the alternative, the two things we need to address to comments to address this United Nations Secretary statement and Prime Minister of statement. By covering this issue, by both these statements, we need to go for the two things. One is renewable energy. So we need to look for the energy production pathway without the use of fossil fuel. And second is the fossil fuel cannot be controlled directly. Not only fossil fuel, even from our ACs and other electronic appliances, also carbon dioxide is emitted. Okay, even through the war, huge amount of carbon dioxide is emitted. So we need to find a way to mitigate, or mitigate means we have to collect that polluted air, that is carbon dioxide, and we have to use it for some other purposes, or if we can able to convert the CO2 into some other useful form of products or any other. These two things are very important in the current context. Yeah. So when you discuss the renewable energies, there are so many renewable energies are there: solar, wind, other energies are there. So among them, hydrogen-based energy is become popular in today's generation. So hydrogen Okay, so like LPG, the LPG auto we know, right? So like instead of LPG, if we can purge the pure hydrogen gas into a particular auto, particular scooter, it will run. The main advantage in hydrogen-based cars and vehicles is that they will not emit any smoke, which means the CO2 emission from that vehicle will be zero. Okay, that is why the hydrogen-based cars and hydrogen-based vehicle transport is everything. Lot of automobile companies even in Changon nearby our in India also focusing on how to implement this kind of hydrogen fuel in their cars. Okay, the heavily most of the R&D department that I know in and around our area working on working on constructing the devices and the mechanistic parts to work in parallel or in accordance with the hydrogen fuel. So there are a lot of research were going on. So the hydrogen is kind of an alternative fuel in the futuristic society because it is eco-friendly, it is green, it is a light element. In the periodic element, hydrogen atomic number is 1, which means it is the lightest element we have in the periodic table. So that is why its gravimetric energy density is very high. So you can push more amount of hydrogen in a more amount of hydrogen, and it will not weight anything. So for example, let us consider a very high let us consider very high transport machines or very high JCB, that kind of machine. So even for petrol also we need to fill 5 liters or 7 liters, 10 liters. That itself weight a lot, right? So think about, you insert some fuel, but that fuel will not give any weight at all. So which means the friction will reduce, the efficiency of the vehicle, everything will increase. So this is the one option. Another, volumetric density also very low. So we can high. So volumetric density also very low. So we can purge amount moles of hydrogen into the particular space of volume. And the production of hydrogen is mostly based from the water. Okay, so the source of hydrogen is nothing but water. So 75% of our earth is filled with water. So if we can find a way to convert this water into a chemical into the hydrogen, then we can find a pathway to produce more hydrogen fuels for the future vehicles and transports. And these also have a low ignition energy, high burning velocity, and high combustion efficiency. So these things are very important in the industry perspective for the metal cutting and the metal reforming possibilities. So when we discuss about the hydrogen as a fuel, which means converting water into hydrogen, two methods are dominant. One is electrocatalytic way or photocatalytic way. Okay, so the splitting of water into hydrogen is not very new. It's a very old way, but yes, I will also explain why later. But this study is related to this kind of electrochemistry or electrocatalysis. Is the guy who proposed the idea of how much charge one mole of electron can carry. So that's what he claimed, Michael Faraday. And then the Volta comes and he said, how, for example, if you insert one metal into a liquid, for example, you need to apply voltage, right? So for example, the work function, you know, work function for the metal, right? So if we apply one work function, if you apply energy equal to the work function, the metal surface should release an electron. But it takes some extra energy more than the work function to release the electron. So he claimed that extra over what we call as over potential. We will discuss that about later in the section. So he found the over potential issue. So the extra energy each surface take to release electron in the electrode electrolyte interfaces. And then the Julius Duffel combined Volta's ideas and Faraday ideas, and he proposes the how to calculate the kinetics of the reaction. So, for example, I put some chemical electrolyte and I put some electrode and then I apply electricity. So, how the particular electrochemical, how fast that particular electrochemical reaction will happen or not, that will be determined by the Tuffle slope. Like if using the chemical equation V equal to A plus B logarithmic log of modulus J. So J is current density, B is the Tuffle slope, and A is the logarithm constant, random constant, and V is the voltage. So using this equation, we can calculate the value of B, which is nothing but the Tuffle slope, and from the Tuffle slope value, we can determine how fast the particular electron chemical reaction will be. Okay, and these three guys contributed heavily for the electrocatalytic water splitting, especially but Honda and Fujishima are the modern day scientists in the 1972 or 75, I guess. They proposed the idea of photocatalytic water splitting. You don't need to apply any electricity. Okay, you prepare the material and mix the material with the water, apply the sunlight or apply light. Then automatically the with the help of light energy itself, the water will convert it into hydrogen. So that's what the Honda and Fujishima reported in 1972 in the Nature Journal. And after that, the photocatalytic water splitting also boomed. So in our research group, we focus more on electrocatalytic, but we do some photocatalytic measurements through the collaborator. But in this presentation, I focus more on electrocatalytic water splitting. So the electrocatalytic water splitting is more efficient and it is scalable. Okay, completely scalable. You can it's not only laboratory type device. Okay, like a battery, the battery can be produced in a factory, and that battery can be incorporated in laptop or device, any devices, right? Likewise, the electrolyzer is also a scalable product, so we can make in a bigger way or a high product based on the energy efficiency you need, energy how much gigawatt or kilowatt you need. Based on that, you can make engineering, you can engineer the design, and you can use it for production of hydrogen. And stability, versatility, and faster reaction kinetics, and purity. So the purity, in the sense, there are three types of hydrogen is there. One is gray hydrogen and green hydrogen and black hydrogen are there. So, okay, so this electrocatalytic means of producing hydrogen is called green hydrogen, because it through this process there will not be any production of carbon dioxide, especially I think in the alkaline electrolysis. Maybe when you you go for any pollutant based electrolysis, on that electrochemical reaction, sometimes CO2 can be released. Okay, but in the pure alkaline electrolysis, there is the possibility of producing hydrogen. The possibility of producing CO2 is very low. That's why we trying to say electrocatalysis is one way of producing green hydrogen, which means zero carbon dioxide. So, like I said, the electrocatalysis, or what we call device, the whole system is what we called as electrolyzer. So it is completely scalable. So electrolyzer is nothing but a battery. Like the battery, right? What battery does? It converts the chemical energy into electricity and store it. Okay. So, or same way, the electrolyzer convert electrolyte into a chemical fuel, or water into a chemical fuel. So the chemical fuel is nothing but hydrogen gas, or maybe oxygen gas, or maybe any other form of gases, okay, which can be used as a fuel for certain vehicle or reactions or anything. So in the electrolyzer, we are usually have a anode and cathode which are immersed in a electrolyte, that is solution. So in the anode side, the reaction will electrochemical reaction will take place, namely oxygen evolution reaction. In the cathode side, the reaction will take place, namely hydrogen evolution reaction. So in this case, we use the water into hydrogen and oxygen, right? So the dissociation or the water reduction process is not a spontaneous chemical reaction. So if it is a spontaneous chemical reactions, if we just simply insert these things, the chemical reaction will happen, right? But this is not a spontaneous chemical reaction. It needs the Gibbs energy of around 237 kilojoule per mole. So if you convert this 237 kilojoule per mole in terms of voltage, normal voltage, so that value will be 1.23 volt. So which means if you want to convert, or if you want to reduce the water into hydrogen and oxygen, you need to provide a minimum potential of 1.23 volt. Okay, so that is the thermodynamical bottleneck you have to face here. Okay, then what is this OER and HER? So we mentioned that in the OER, oxygen evolution reaction takes place. Sorry, in the anode, oxygen evolution reaction takes place, and the cathode, hydrogen evolution reaction takes place. So, for example, M means a metal. Okay, usually metals are used in the earlier days in the electrolysis. That's why they put M. So, if you put a metal in the alkaline electrolysis, alkaline means usually potassium hydroxide or sodium hydroxide. OH minus. So MOH will join MOH, M plus OH minus will join MOH, and then it will it undergone 4 electron pathway. Okay, the 4 times the electron comes out of this reaction. So it undergone a 4 electron pathway to yield the oxygen gas. But in this case, see, it's a cathode is the hydrogen evolution reaction, which means it consumes the electron. So anode will emit the electron, cathode will consume the electron. So here you see only electron present in 2 parts, which means it's a one electron pathway or 2 electron pathway. For example, if the electrode took Walmer-Tuffle mechanism, it is a 1 electron pathway. If it takes a Walmer-Hevrosky step, it takes a 2 electron pathway. Anyway, the problem thing is it sluggish reaction. So oxygen evolution reactions are always called a sluggish reaction, but because it involves 4 electrons, whereas HCr involves only 2 electrons. So yeah, so the whole process occurring in the electrolyzer is what we called as adsorption, not the absorption. So there is a huge difference between absorption and adsorption. So adsorption is a surface process, but absorption, we some of us may work in dye degradation and those things, right? So in that case, what will happen? Entire absorption curve will change, right? Because the absorption is a bulk property. So whatever changes happen as a process of absorption will change the whole material property. But adsorption is a surface process. Only on the surface of the particular material only this adsorption physical process will happen. So in that quantity is called adsorbate and adsorbent. So in the case of adsorbent, is nothing but our electrocatalyst material, whether it's a cathode material, cathode material or anode material. So in that case, adsorbate is and the energy of this D and S band. If the S band have a volume wise, it's a very vast, but distribution, the number of electrons is very low because S can hold only 2 electrons, right? So that is why the density of states in the y-axis is very narrower for S band. But the d electrons can hold 10 electrons, right? So that is why the density of states, in the density of states value is higher for the d band. Okay, but we also studied the Fermi level, right? The maximum energy can electron can occupy at absolute 0 Kelvin temperature. So that Fermi level will be fall near to the D band or far to the D band. That is very important. That will determine your catalytic activity. For example, let us say in the case of rhodium, which is high performing material, right? So this is the D band. So this is the D band, and near to the middle of the D band, the EF, the Fermi level is there. So which means below the Fermi level, we know the electrons will be filled. Above the Fermi level, the probability is less than 0.5. Okay, so then most of the electrons will be empty. Orbitals will be empty above the Fermi level. So which means this is what we called as anti-bonding orbitals, and this is the electrons filled orbitals below the Fermi level. We claim as bonding orbitals. So these anti-bonding orbitals are very important because when the adsorbate come to contact the surface of the electron, so that adsorbate will try to interact with these anti-bonding orbitals. So if there is a vacancy or if there is a availability there in the anti-bonding state, the electron will be interacted and the electrochemical reaction will taken place easily. Okay, so if there is no vacancy here, which means no active site is here, means that for example, let us say the silver case. Okay, in the case of silver, the Fermi level is false here, and below the Fermi level, everything will be filled, which means completely D band is filled. Even in the S band, also more than 70% is filled. So only very few amount of S band is removed. So in this case, the interaction of the adsorbate, the interacting space for the adsorbate will be very limited. Okay, and especially the energy of the S band is very higher. So which means the intermediate energy, for example, I already mentioned, right? For intermediate to attach with the material surface, it needs to possess certain energy, right? If it is a D band, it needs to provide the minimum amount of energy because the D band is very outermost and the density of states also energy also lower. But if it is a S band which is deeper, so it needs to provide more energy to interact with the electron. So from this analogy, you can notice one thing: whenever the D band is partially filled, the Fermi level falls on the D band. Whenever the D band is completely filled, then the Fermi level will fall above the D band. So from this, we can notice one thing: whenever the D band is partially filled, we will have a better catalytic activity. We can analogously we can take that statement. So in that case, which table or which group in the periodic table have partially filled D band? None other than transition metals. So you see the manganese, iron, cobalt, nickel are all having partially filled D band orbitals, which means the probability of having the Fermi level in the middle of D band is very high. Okay, and obviously the cost wise also, transition metals are so cheap compared to platinum and other rare earth based elements. So let us compare this with the ultraviolet spectroscopy. I will go quickly because I need to discuss some more. Ultraviolet spectroscopy, from that we can also calculate the status of the outermost electron. So for example, this part is a secondary electron and this part is the density number of electron, or this intensity is related to the proportional to the number of electrons in the D band, and this is the Fermi edge. So from below the Fermi edge, the orbitals levels of the electron density is here. So usually for the work function, what we do, we calculate the energy difference between these bands, the D bands, and subtract it from the input source, that is helium, and from that we calculate the work function. So for example, let us, we even practically we can, if we have the UPS facility, we can practically we can observe. So for example, in the case of silver, as we mentioned previously, the Fermi edge is here. So which means the D band is here, which usually have a higher intensity compared to the S band, but which is very far away from the Fermi level position. But in the case of rhodium, see the Fermi level is overlapping inside the D band. So which means inside the D band, the Fermi level is present. So which means the distance between the middle of the D band and the Fermi level is very minimum. So for example, we can take another examples like nickel. If you take a nickel, which is one of the transition element, so the Fermi level falls into the D band. But in the case of copper, it is far little away from the D band. But in the case of zinc, it is very far away from the Fermi level position. So if you plot a graph between difference between the D band center to the Fermi level, the distance will be very minimum for nickel, marginally higher for copper, very higher for zinc. So that is why nickel is one of the widely used element in the electrocatalysis application. Okay, and it is also cheap. So that is why the nickel based material is used. Even so, for most of the people using nickel substrate or nickel foam for the electrocatalysis application, because it is one of the transition element. Its D band center is somewhat near to the Fermi level position. Because of these reasons, people using transition metal. So that is why the multi metal or multi component, multi elemental things are very important. With that, we can change the electronic structure. We can dual active sites, and dual active sites in the sense we can push the Fermi level near to the D band center, so we can increase the active sites. So based on these merits, we are employing monometallic or multi-elemental material. So if you have a more interest, if you want to know more about the different kinds of material employed for energy conversion application, especially OER, HER, and ORR. ORR is kind of the oxygen reduction reaction, so which is necessary for metal air batteries. Okay, so we are not working, we are just starting, but we didn't get any results so far. We are working on that also. So if you want to learn about these things, I recommend you to study this research article, review article we published recently. Interested people can look over. So the bifunctional catalyst, electrocatalyst is another one of the approach we actively employed in our research work. So for example, if you make an electrolyzer, okay, if you use some kind of platinum, the rare earth metal, your overall cost will be higher, right? So at the same time, if you use different kind of materials for OER and HER, then again the cost will be higher with respect to the element presence, and the design wise also it will be complicated. But you just think about using a same material as anode as well as cathode, so the design concept will be easy, compact, and the cost also will be reduced. So that is the one of the aim. One material can perform both chemical reaction well. So that is why those kind of materials are called bifunctional electrocatalysts, which can perform both OER and HER. And sometimes people used to call bifunctional electrocatalysts as OER and ORR. So in that case, one electrode can perform OER and ORR, which is useful in metal air battery applications. So the electrocatalyst evaluation, there are so many parameters, several parameters are there to evaluate the quality of the electrocatalyst. One is over potential. So the over potential is the extra potential taken by the electrode in addition to the thermodynamic potential. The thermodynamic potential is the theoretical potential, right? So in addition to the theoretical potential, based on the environment, based on the electrolyte charges, and based on the mobile ions present in the electrolyte, it will take additional extra voltage to perform the chemical reaction. So that over potential should be as minimum as possible for an electrode to perform better. So Tafel slope, I already mentioned, it's about the reaction kinetics. From the equation of V equal to A plus B log mod J, we can calculate the Tafel slope. And electrochemical active surface area is kind of in the surface of the electrocatalyst, how many surface sites are available for the interaction, which is very much related to the bonding orbital, anti-bonding orbital, D band theory we discussed, right? which is related to that. And Faraday efficiency is the direct conversion, how many electrons I supplied in the form of voltage and the form of electricity, and how many gas are evolved. So this ratio is what we call as Faraday efficiency. But only performance not alone is enough. The stability, robust nature of the electrode also important. How long the electrode will sustain. So that to understand that we need to do chronopotentiometry, chronoamperometry, and the continuous cyclic voltammetry. And from these methods, we will allow the electron to perform the electrochemical reaction for a constant current, for a constant volume, for a long period of time, like 100 hours or 500 hours, like that. So after that, if the electrode remains stable, then we can call that as stable electrode. And in this discussions, the most trending thing in the electrocatalyst is to use heterostructure and composites. So the heterostructure and composites are very helpful in optimizing the D-band center, Fermi level near to the D-band center, so that the absorption energy can be reduced and the active sites can be increases. Especially heterostructures are useful when you deal with the atomic level or nanoscale level materials. And but if you work on powders, like if you work on bulk powders, you can go for composite material. So the because the composites also very much important, because when you speak of scalable things, bigger size electrolyzer, we cannot simply coat in situ coating or atomic level coating, right? So we need to, for the larger scale operations, we need powders or ink type catalysts. So for those applications, composites are highly preferred. So with this, I will like to discuss some notable works from our group. I will go quickly. If you have any doubt at the end of the presentation, I will explain. So one of the work we performed is incorporating tin sulfide and nickel cobalt oxide in the form of a heterostructure. So this the idea is tin sulfide or most of the sulfide anion based transition metal chalcogenides are very active HCr material. Okay, but the problem is that they can easily leach out into the solution. And whereas the nickel cobalt oxide based spinel oxides are very popular OER candidates. So our idea was combining these two in the form of heterostructure to realize a bifunctional electrocatalyst. So in that case, we also observed some shift in the tin peak, which is related to the bonding of tin with oxygen present in the nickel cobalt oxide. So with that, because of this interfacial bond, the heterostructure is highly stable and perform well in the alkaline electrolysis. So this work we also did DFT theory. So from the DFT theory, we calculated which site in the heterostructure provided lowest absorption energy. So for example, in this case, we found that the sulfurs present on the tin sulfide. Okay, the tin sulfide is in the top, nickel cobalt oxide in the bottom. So we have a sulfur orbital or vacant sulfur orbital present on the surface of the heterostructure possess the lowest absorption energy, and that helps to achieve better HCr performances. So this, with the help of a collaborator, we did that. And in the case of over potential also, it achieves 154 millivolt per 20 milliampere current, and the Tafel slope also 110, which is moderate, not so great. And over potential for the OER also 302, 20 milliampere per centimeter square, which is quite good, because over potential anything above 300 is below 300 is very good, and ours is almost near 300, so it's not a bad data. Duffel slope also 160 milliwatt per DEC, which is also not so great compared to our recent results. And the electrochemical surface area for this heterostructure is calculated, and this work is completely in situ fabricated, not a powder based catalyst. And we also applied same material as the cathode and anode in a two cell electrolyzer without the membrane, which exhibit a potential of 1.57 and stable for more than 25 hours. So this work is published in ACS Energy and Fuels Journal. In another work, we are not focusing on bifunctional, but we are planning to make a one HCr material for all pH solutions. So in the universal pH means we take an acid which is low pH, and neutral 7 pH, and alkaline, as usual, above 7 pH, around 8 or 10 pH, 11 pH. So in that pH, different pH levels, we want to find a single HER material which can perform well in all these three medium. So with that, for that we take a help of hematite. So hematite is one of the strongest material, right? Iron cobalt metal, nickel iron cobalt, cobalt iron cobalt, copper iron oxide, nickel iron oxide, the cobalt iron oxide. These are hematite, very famous for stable nature, and this that is also a moderate HCr performance they give. So we couple this hematite with the tin sulfide, and that this material is performed really well in buffer solution, that is neutral pH, and alkaline and acid. So this is the comparison of a HCr ore potential in alkaline medium, acid medium, and a neutral medium. So in the case of neutral medium, we know the radicals are very limited. No radicals will be available in neutral pH. That is why the ore potential is relatively higher compared to alkaline and acid. So for this also, we found that the tin and the above hematite based oxide interact with the interfacial bond of tin sulfide, tin oxide. So these interfacial tin oxide bonds not only stabilize the structure, but it also increases the oxygen vacancy in the whole heterostructure. Because of the increased oxygen vacancy, the conductivity is increasing. So that is why the electrochemical impedance spectroscopy showed a very narrower, very low contact RCT value. As a result, we get a good performance in all the electrolytes. So this paper is published in Applied Surface Science. And in another work, we take urea. Okay, so for example, instead of taking the alkaline medium, which means KOH based water, we added some impurity in the KOH, like urea, 0.33 molar urea. So this idea is related to pollutant remediation. So the urea is one of the byproduct released in most of the fertilizer company. Okay, so the water will always contain with water. So the if we can take such kind of polluted water and we can use it in for the hydrogen production, it not only generated chemical fuels, but it also remediate that pollutant in the form of useful gases or useful product, right? So in that perspective only, people employed urea. We are obviously need not taken the polluted water from the industry, but to mimic it, we are incorporating 0.33 mole of urea into a alkaline water. It's a simulated polluted water. Okay, so in that case also we employed nickel iron layered double hydroxide, which is a very famous group for OER, highly active the transition metals. Nickel iron LDH is a very popular guy for OER material. So we added it nickel Na3S4 polyphase nickel sulfide, and it exhibit very good properties in overall urea electrolysis. So for example, the urea, it exhibit a potential of 1.34, which is a very good value in the context of UOR, and Tafel slope also less than 100. So in the previous case, we always reported above 100. Nowadays, we reported less than 100, which is very good, which means the reaction is faster. Okay, in the case of HER also is 119 millivolt, and the lowest value is around 139 for the Tafel slope, but still it's lower, but it is not a pure medium, it's a pollutant medium. So in that case, this value is somewhat okay, and the corresponding CDL and other things also very good, and especially this material is kind of suitable for this kind of polluted water rather than alkaline water. So the same electrode is employed. For example, this is you can see here, the polluter 1 molar KOH is the alkaline. This is the two cell graph, and after the urea infused, very low potential is required for the current density generation. This is indicate the urea intermediates actually having a low intermediate energy compared to the oxygen intermediate. So that's why it's quickly attached with the electrode surface and produce current density here. So this work is published in International Journal of Hydrogen Energy. And last electrocatalyst work I want to discuss is seawater electrolysis. So I mentioned in the previous slide, right? In the introduction slide, I mentioned 75% of water in the earth is 75% of the volume in the earth is water. So if we can able to find a way to convert it to a hydrogen, then we can claim hydrogen as a completely renewable energy resources. So in that case, the problem is we are not able to directly convert the seawater into hydrogen because the seawater contain lot of salts, especially sodium. Okay, sodium, calcium, these salts will be there. So if we can do the electrolysis, these salts will contaminate the electrode surface. The stability of the electrode will be a big question. Okay, and once these elements corrode the surface of the electrode, the current density will drastically drops down, and the hydrogen generation will be reduced significantly. So we need to find a suitable material which can withstand this kind of corrosion and produce hydrogen gas. So that is our aim. So in that case, we are taking a help of nickel iron MOF. So metal organic framework is a very popular group of family, especially in the 2024 Nobel Prize also given for the persons who in the chemistry is given for the person who discovering this nickel and metal organic MOF to 15 or 20 years back. And so nickel not only in electrocatalysis, different super capacitor medical field also MOF performing a really good role. So we take a nickel iron MOF. In that we do some tailoring with the heteroatom doping. After the two different heteroatom doping, that is material becomes stable for stable in the seawater electrolysis and produce the voltage of 236 millivolt, which is very good for a seawater electrolysis. And HCR also performed in 128, which is not bad category. And the Tuffle slope also really good, especially for the OER. The value is below 60, so which is a very good thing for a electrocatalyst material. And not the problem with the seawater is not the performance, it's the stability. So in order to test the stability, we allow the two cell electrolyzer to run for 100 hours. So after 100 hours, we test the sample with ion chromatography, because the problem is in the seawater or the simulated seawater, we usually add sodium chloride into the KOH. So the sodium chloride, the sodium can also corrode the surface of electrode, or the chlorine. The main issue is chlorine. Okay, the chlorine oxidation potential is very much near to the oxygen oxidation potential. So sometimes chlorine can oxidize. If the chlorine can oxidize, it will create some barrier in the electrode, so it will corrode the electrode. So we need my electrode will select only oxygen intermediates, avoid chlorine intermediates. So for doing the if my material doing that or not, I need to inquire. So for inquiring that, we need to take the help of ion chromatography. From the after 10 hours, we see there is no, this only peak is given for unreacted chlorine. So the remaining, there is no peaks are there for the higher version or the different oxidation version of chlorine, which indicates that the chlorine present in my electrolyte after 100 hours also not reacted, which means these chlorine are not selected by the electrode for the oxidation. So which means my material is highly selective and stable for seawater electrolysis. This work is currently under review in Journal of Metal Chemistry A. And then we'll enter into the carbon dioxide photo reduction. Maybe sorry, I will take extra time. I think maybe 5 minutes I will finish. Okay, the carbon dioxide photo reduction, as I mentioned previously, we also have to reduce the CO2 generated in the society in order to in order to help the climate change, or in order to reduce the greenhouse effect. So if we can able to use the polluted carbon dioxide value added products, that will be kind of environmental remediation, right? We help the environment as well as we use the pollutant into the form of useful products. So in that case, the CO2 can be converted into a value added products like methane. Methane is a natural gas. We can use it for LPG, other purposes also. And methanol. Methanol is also useful for solvent and other application. This is formaldehyde. So the formaldehyde is used in fertilizer industry. Carbon monoxide is also dangerous, but less dangerous than carbon dioxide. And formic acid also useful in several industrial applications. So if we can convert carbon dioxide into any one of these useful products, it will be useful for the sustainable energy society. So that is the main aim. So the CO2 reduction I already explained. We can done it through photo reduction, applying the light energy. We can convert the carbon dioxide into useful products, or electrode reduction by applying electricity, like how we did for the cell electrolyzer, right? So in the same way we have to follow. We have to take the electrode, immerse in a liquid, immerse in an electrolyte, but we have to purge the CO2 gas continuously into the system, and then we allow the electricity to run. So that the hydrogen evolution reaction will take not takes place, only the carbon dioxide reduction will takes place. Okay, but we are not doing that in our lab. Electro reduction of carbon dioxide is not doing that. Only we do photo reduction of carbon dioxide. And for example, for converting the CO2 into carbon other forms of products like carbon monoxide or other forms of value added products, it needs certain energy. That energy should be given by the catalyst. Okay, that's the role. Again, the carbon dioxide photo reduction is not a spontaneous reaction, so it needs external energy. That external energy we can give in the form of electricity or in the form of photons. So especially here we want to give in the form of photon. For that we need to select the catalyst material with the proper band gap, which in between 1.8 to 3 electron volt. So if you take a material, semiconductor material in this range of band gaps, so once the electrons are once the etc are created in that, and the electrons are going to the conduction band, right? So these conduction band electron can impart energy to the CO2, and because of that electron because of the energy received from the conduction band electron, the CO2 will reduce into carbon monoxide or any other useful products. So that is the aim. So this idea of photocatalytic carbon dioxide reduction or photocatalytic water reduction is proposed by Honda and Fujishima in the 1972. For example, in the case of water, the idea is simple. So if you apply photon, it will reduce into hydrogen or oxygen gas. But the problem in CO2 is the CO2 can be reduced in any one of the 6 products mentioned here, either as a COOH, acetic acid, formic acid, and carbon monoxide, and formaldehyde or methanol or methane. So any one of these product can become. That is depending on the selectivity of the material. So if the material band gap in such a way and material absorption energy is such a way so that it can produce carbon monoxide. Some material can directly produce methane. So we need to find the material one by one to get the selectivity of the material. And for the electrocatalysis application, the material photocatalytic CO2 reduction application, the light, it should absorb high light, and the band gap positioning, especially the top of the conduction band, bottom of the valence band, should be lie near to the water oxidation potential or water reduction potential for the photocatalytic application. So, but if you work on carbon dioxide reduction, your conduction band top energy should be near to the methane product, near to this level. For example, see, the conduction band energy should be higher than these energy levels. So that's why any one of these product, because when the conduction electron traps imparts energy to the CO2, that's why the energy CO2 will reduce in any one of these forms. So if these conduction band electron is lower than this value, then the CO2 reduction will not take place. Okay, for band gap positioning, high surface area of the catalyst is very important. High the charge carrier separation. This is a very important, because once the electron hole pairs are, I give a photon in the band gap, electron hole pairs are generated, and the electron hole pair should be separated like in the solar cell. So then only the energy will be imparted to the CO2. So for that, what we need a longer lifetime of electron hole pairs in such kind of material. So in order to achieve the longer lifetime of electron hole pair, we need to go for the different designs of electron, because one material, it's a fixed electron hole pair lifetime, right? So we cannot expect that material, one single element can perform a very good activity for CO2 photo reduction. So that is why the heterojunction, in the heterojunction, we can take a one p-type material or n-type material, we can sandwich them. Then the interface, we have the electric field, and that electric field helps to separate the electron and hole pairs so that we can generate effective CO2 reduction. So which is very, very similar to solar cell activity. But in the case of S-scheme heterojunction, we have a two material, one material conduction band should be higher than the another material conduction band. So in between these two conduction band, there is a depletion region will be created, and that depletion region will effectively deplete the electron and hole pairs. In the Z scheme, the valence conduction band of one material will interact with the valence band of another material, and in between there is energy barrier will created, and this depletion region will separate the electron and hole pairs effectively. So based because of these heterojunction schemes, the CO2 photodetection can be effectively increased. And this is the photocatalytic reactor setup. This is the setup we are used for CO2 photo reduction. Obviously, it's not available in SRM. Through our collaborator, we do the results, Chonbuk National University. And only one example we are going to discuss for the CO2 photo reduction due to the time. And for that, we take a nickel and LDH. So the layer double hydroxide is very known for high CO2 absorption and high ionic conductivity. So because of that, we take this material. But unfortunate thing is nickel and LDH charge separation or the electron hole pair lifetime is very, very low. So that is why I want to add one more material into nickel and LDH, which has a good band gap of absorbing the photon, and also it exhibits very high electron hole pair lifetime. So in that way only we choose silver sulfide. So we mix the silver sulfide, we decorate the silver sulfide on the edges of the nickel iron hydroxide. Once we attach the silver sulfide, there is a compressive stress and compressive strain is generated. Because of this compressive stress and strain, the nickel ion LDH exhibiting higher ionic conductivity and high electrical conductivity, so that the electron hole pair also can be increased significantly because of the strain generation. And as a result, the carbon dioxide is effectively converted into carbon monoxide and methanol. The 88% of selectivity is for CO, and only 12% of selectivity is for the methanol generation in our material. And we also tested the sample for 5 different cycles. In all the 5 different cycles, our photocatalyst material exhibit very stable nature. And in the apparent quantum yield measurement also, the maximum AQI is observed around 350 to 420, which is the region very much overlap with the UV absorption spectrum of our LDH Ag2S composite, which indicating that this combination, this interface between silver sulfide and nickel LDH plays a very crucial role in generating or reducing this carbon dioxide. That is why the AQI is very much higher near to the absorption edge of the composite material, absorption band of the composite material. So from the XPS also, we noted notable shift in the nickel center and the iron catalytic center, indicating drastic electron transport variation between these composites, which helps to get higher electron hole pair lifetime. And oxygen from the EPR analysis also, we understand that the stress created in the nickel and LDH increases the oxygen vacancy, so that the conductivity also increases in the composite system. So the direct data for the electron hole pair lifetime is time resolved PL. So from the time resolved PL, there is a clear indication that compared to nickel and LDH and Ag2S, there is a drastic and notable increment in NFAS15. That is 50% Ag2S incorporated nickel and LDH, indicating 7.7 9 nanoseconds. So this increased lifetime helps to achieve effective carbon dioxide reduction. And from the valence band XPS and Marz-Schottky analysis also, we confirmed both materials are N-type in nature. And valence band analysis also, we calculated the valence band bottom value of the individual materials, Ag2S and silver, nickel and LDH. With that help, we draft the energy band diagram. As per the energy band diagram, our material perform a S-scheme type of heterojunction, and our conduction band bottom value is very much near to the composite effective conduction band value is very much near to the CO2 that is 0.53. So that is why our material exhibit very high selectivity to CO generation, and the very next is methanol. So that is why the very few 12% selectivity is given for methanol. So with this, we confirm the S-scheme generation of our material catalyst system and its performance in CO2 reduction activity. So with this, I want to summarize this talk. So in this presentation, we discuss about the importance of energy landscape, why we need to go for hydrogen research or hydrogen production research, and why we need to look for reducing the CO2 generation in the society in order to support the global warming or reducing the global warming actually. And then we enter into the fundamentals of electrocatalysis, different types of materials of family, and various evaluating parameters we discuss. Especially, we discuss about the D-band theory. Why how the D-band theory reinforces the search for low-cost electrocatalyst research, and we also discuss some notable works from our research groups. And we also discuss about the fundamentals of CO2 reduction. So, in the case of CO2 reduction, how the CO2 gets reduced with the help of conduction band electron energy, and we discuss these things and materials design strategies, heterojunctions of CO2 heterojunctions, different types of heterojunctions used for CO2 reduction we discussed. And finally we discussed about the one example we regarding the CO2 reduction and how to understand the data for the CO2 reduction we discussed. And with that, I want to summarize this talk. Before moving to the thank you slide, I want to introduce our CMAT portal. So this is the Center of Excellence in Materials for Advanced Technologies, the center I belong to. In that, we have 6 or 7 instruments we have, and from July 1, we currently open it for external users also. So you can also use these instruments, and you can register, and you can pay, and you can register. You can take measurements for this system by using a slot. Okay. And if you have any doubt regarding the slot booking and other things, also you can contact me anytime. I will help you. Okay. My details are also in that same website. You can refer that. Okay. And with that, I want to conclude my talk, and thank you one and all for listening to this presentation. And I'm happy and willing to take the questions from you. I will try my best to answer. Thank you. Yes, ma'am. Someone posted in the chat box. Could you share your questions? I'm happy to answer if you have any. Thank you, Dr. Raja, for your nice words. And yeah, thank you. And if you have any doubts, also you can ask. Thank you. Thank you. Thank you for the. Thank you. Thank you. Thank you, everyone. Thank you.